We use linked lists to store a list of objects in sequence. But unlike arrays, linked lists can grow and shrink automatically. As you can see here, a linked list consists of a group of nodes in sequence. Each node holds two pieces of data. One is a value, and the other is the address of the next node in the list. So we say each node points to or references the next node. That's why we refer to these structures as linked lists, because these nodes are linked together. We call the first node the head and the last node the tail. Now let's look at the time complexity of various operations. Let's say we want to find out if our list contains a given number. We have to traverse the list starting from the head all the way to the tail. What is the runtime complexity here? It's O of n, because the value that we are looking for may be stored in the last node. That is our worst case scenario, right? What about looking up by index? Well, unlike arrays where items are stored sequentially, the nodes of a linked list can be all over the place in memory. They may not be exactly next to each other. That's why each node needs to keep a reference to the next node. For this reason, unlike arrays, we cannot quickly look up an item by its index. We have to traverse the list until we find that item. In the worst case scenario, that item can be at the end of the list. So once again, here we have O of n. What about insertions? Well, it depends where we want to insert an item. If we want to insert a new item at the end, we simply need to create a new node and have the last node or the tail point to it. We should have a reference to the last node somewhere so we don't have to traverse the list every time. Now we need to have the tail reference this new node. So inserting a new item at the end is an O of 1 operation. What about inserting at the beginning? What do you think is the runtime complexity here? Pause the video and think about it. Here's the answer. It's an O of 1 because, again, we should have a reference to the head or the first node. So to insert a new item at the beginning of the list, we create a new node, link it to the first node, and then change the head to point to this new node. Again, this is very fast. Unlike arrays, we don't have to copy or shift items around. We simply update the links or references. Now, what if you want to insert an item somewhere in the middle? Let's say after the 10th node. Well, first we have to find that node. That's an O of n operation. And then we have to update the links, which is an O of 1 operation. So inserting an item in the middle is an O of n operation. Now let's talk about deletions. I want you to pause the video and think about 3 scenarios. Deleting an item from the beginning, from the end, and from the middle. Draw on a piece of paper how the links should be updated. Also, calculate the runtime complexity for each scenario. This is very important. Make sure to do this little exercise because later on, you're going to code all of this. If you don't understand these concepts, you're not going to be able to code them. So pause the video, do the exercise. When you're done, come back, continue watching. All right, here are the answers. Deleting the first item is super fast. We simply set the head to point to the second node. That's an O of 1 operation. Now, we should also remove the link from the previous head so it doesn't reference the second node anymore. Why? Because if we don't do this, Java's garbage collector thinks this object is still used, so it won't remove it from the memory. That's why we should unlink this object from the second object. What about deleting the last item? This one is a bit tricky. We can easily get the tail, but we need to know the previous node so we can have the tail point to that node. How can we do that? We have to traverse the list from the head all the way to the tail. As soon as we get to the node before the last node, we keep a reference to it as the previous node. Then we'll unlink this node from the last node and find and have the tail point to the previous node. So the runtime complexity here is O of n because we have to traverse the list all the way to the end. What about deleting from the middle? Again, we have to traverse the list to find out the node as well as its previous node. We should link the previous node to the node after this node, and then remove this link so this object gets removed from memory by Java's garbage collector. Again, here we have an O of n operation. Next, we're going to work with linked lists in Java.